Okay, so this is from the 2010 test. So let's see, if you flip back, it's about 3, 4, 5, 6, 7. It's 8 pages back, and it's on the back of that 8th page. Up at the top it says 2010, and it's number 4. So it was the first question in the non-calculator portion that year, because 2010 there was still 3 calculator, 3 non-calculator. Now there's 2 and 4, but this might have been the first year that they put it on the non-calculator portion. I'm trying to remember. There was one year where, oh no, it was on the non-calculator portion that year too. There was one year where, like, and every year before that it had been on the calculator portion, and I told my students it would always be on the calculator portion, and then it wasn't. So it has shown up on the non-calculator portion several times since then. Okay, so this says, let R be the region in the first quadrant bounded by the graph of y equals 2 square root of x, the horizontal line y equals 6, and the y-axis is shown in the figure above. So this is y equals 6. So which means that this must be y equals 2 square root of x. And then we've got the y-axis. So part A, you have to find the area of that. So we talked about how to do that this week. Yeah, I think that's what we did on Tuesday. So when you're finding the area of a region that's enclosed by 2 curves, we're going to integrate from 0 to 9. Those are the x values where the two, like, that contains the two x values that contain that area. So from 0 to 9. And we do top curve minus bottom curve. So we do 6 minus 2 square root of x dx. The top curve is that y equals 6 line, and the bottom curve is that y equals 2 square root of x line. So pretty easy to set up, and so now we just need to integrate it. I'm going to come down here and get myself some room. So I'm going to rewrite that as 6 minus 2x to the 1/2. Because remember, we don't have any rules for square roots. We always rewrite square roots using exponents. And then we integrate. So 6 becomes 6x minus 2 times, and then x to the 1/2 becomes x to the 3/2, because we add 1 to the exponent, divided by 3/2, which is the same as multiplying by 2/3. From 0 to 9. We don't really have to worry about the 0, because when we plug 0 in, these will both be 0. Right, 6 times 0 is 0, 0 raised to anything is 0, and then 0 times anything is 0. So really we just have to worry about what we're going to get when we plug 9 in. So we get 6 times 9 minus 4/3. Alright, 2 times 2/3 would be 4/3. 4/3, 9 to the 3/2. So 54 minus 4/3 times. Alright. So 9 to the 3/2, that means the square root of 9 cubed. The bottom number is your root, and the top number is your exponent. So this is telling me to do a square root and then cube what I get. So the square root of 9 is 3, and then 3 cubed is 27. 4/3 times 27, 3 goes into 27 9 times. And 4 times 9 is 36. So 54 minus 36, which is 18. Look this up. 2010, number 4. This is worth 3 points. 1 point for setting it up correctly, knowing what the bound should be, and that it's top curve minus bottom curve. 1 point for actually integrating it and getting what the antiderivative would be, and then 1 point for plugging in and getting the answer. So 3 of the 9 points on that one. So not too bad. All right, all the fractions and the fraction exponent make it kind of messy, but it's not that bad. Okay. Number 2, write but do not evaluate. So this one you just have to set it up. You don't have to actually solve it. Write but do not evaluate an integral expression that gives the volume of the solid generated when R is rotated about the horizontal line y equals 7. Okay, so this is similar to what we did this week, but it has a slight difference. And so it kind of changes the way it gets set up a little bit. So this is the line y equals 6. So y equals 7 would be up here. And we're going to take this and rotate it around that line. It's going to make kind of like a Hershey Kiss with a hole like bore through the middle of it. It's going to have a hole in it because there's a gap between our area that we're rotating and our axis of rotation. So does that make sense? Can you kind of picture that in your head, that there's like a hole in the middle of it? It's like a perfect cylinder has been like bore out of the middle of the Hershey Kiss. Okay, so we're still going to set it up similar to what we did this week, which was we did for horizontal rotation like this, we did pi, we integrated between two x values when we rotate horizontally or around a horizontal axis, and then we had the radius squared. Actually, I did this backwards, but it's really better. And the radius was written in terms of x because we were rotating around an axis like the x-axis, the horizontal axis. Okay, the problem here is that there's not just one radius because of this gap. There's actually two radiuses, and so when we slice this shape, I try to like imagine what it would look like here. It's kind of like, it's got this hole in the middle. If I start, and I just turned it this way so I could see it better. If I start slicing it, the cross sections aren't discs, they're what we would call washers because they have a hole in the middle. Does that make sense? Like each slice, when I slice this, each slice has this hole in the middle, so it makes like a washer like this. Like that. So you have to modify this a little bit. If I have a washer and I want to know just this, I have to find the area of the outside circle and subtract the area of the inside circle. So I have to show that over here that I'm going to take my outside radius and subtract my inside radius. So you actually have two radiuses. You have your radius that's for the outside, and you have your radius for the inside. So you have like a big R, a big radius, and a little r, a little radius. And you have to subtract them. So let's see what those would be. So we're still going from 0 to 9 because we're still stacking our disk set from 0 to 9. So we would say from 0 to 9. Alright, so the radius is always measured from the axis, and the outer radius goes from the axis of rotation to the outer edge of your graph. So what would this be? It's not constant, it changes the whole way up. Well, I know that this is what? What is this distance from the x-axis to that curve? 2 square root of x. And I know that this whole distance is 7 because my axis is 7, is at y equals 7. So 7 minus 2 square root of x would be this. Right? So we would have as our outer radius 7 minus 2 square root of x squared. Minus, now the inner radius is a lot easier. What's the inner radius? Just 1. It's a constant. It's constant the whole way down. It's just that distance between your axis of rotation and this inside edge. And since that inside edge is a straight line and not a curve, this is a constant. So it's just 1. So outer radius squared minus inner radius squared from 0 to 9. And that was worth 3 points. Oh, don't forget the pi. Forget the pi. We would lose a point here. Alright, so this is worth 3 points. So it's 2 points for this part. And it's okay that we wrote 1 instead of 7 minus 6. If what you wrote is equivalent to what's there, it's fine. And then 1 point for this part of it, knowing these two numbers and having the pi. So if I'd have left that pi off, I wouldn't have gotten that point. Does that make sense? So you have to use 2 radiuses if there's a gap between your area and the axis that you're rotating around, which most of the time there will be. Most of the problems on the AP test, volume, you're going to use washers, not discs. Okay. Last one. Region R is the base of a solid. For each y between 0 and 6, so we're going along the y here, the cross-section of the solid taken perpendicular to the y-axis is a rectangle whose height is 3 times the length of its base. Write but do not evaluate an integral expression that gives the volume of the solid. It sounds really hard, but it's really not. It's a kind of like the whole disc and washer method, except we're not creating the volume by rotating. So the things that we're making the volume out of are not circles. In this case, they're rectangles. We can apply the same concept. If we wanted to find the volume of something that was created using circles, we integrated the area of a circle. If we want to find the volume of something that's created using rectangles, we'll integrate the area of a rectangle. So you just integrate area to get volume, and you use whatever area you would have for the shape that you're making. So basically what this looks like. I'll try to draw it. I'm not very good at this, but let's say kind of draw it at an angle so I can see it a little bit better. That's that region R. They're going to have rectangles. That come up out of that region and make like this volume that if you sliced it would be rectangles. Does that make sense? So what we have to do is figure out what are the length and width of those rectangles so that we can integrate their area. Now because we're making these rectangles this way, I'm sorry, we're going to make, actually I do that wrong. They're making them this way. Same kind of idea, but they're making them this way. They're saying perpendicular to the y-axis, so, oh, I'm sorry, thank you. This way. They're saying that the bases are perpendicular to the y-axis, so they're actually doing the rectangles this way, not this way like I drew down here. But same idea. We need to figure out the length and width of those rectangles so we can integrate them. So 0 to 6, because we're perpendicular to the y, so we're stacking our rectangles up from 0 to 6. So we're going to say the integral from 0 to 6. And then the area of each rectangle, so it says the height is 3 times the length of its base in region R. So this is the base. So if we could figure out what this was, we would have the base, and then we would also just multiply it by 3 to get the height. So what is this? This distance from the y-axis to that curve. What if I solve this for x? Y squared over 4 would be this. Right? So that's the base. Y squared over 4. Oh my gosh, I cannot write. Y squared over 4 is the base. Times the height is just 3 times that. dy. So the area of a rectangle is base times height. The base of the rectangles are y squared over 4. The height is 3 times that, so it'd be 3 times y squared over 4, and we would integrate that. So we would get, oops, this is 3 points. 2 points for our integrand, which you don't have to simplify it, but you can if you want to. 3/16, because you've got 4 times 4 on the bottom, and then you've got that 3. So 3/16, and then y squared times y squared, y to the 4th. I don't get what the difference between the integrand and the, oh, I guess having these bounds. Because the integrand is just what's inside the integral, so 1 point would be like for the whole answer here. Does this make a little bit of sense? This is one type of problem that you will see. Like, this will be on there. It may not be rectangles, it might be squares. You know, they might have you rotate in a different direction, but there'll be an area between curves volume problem. So let's look at another one. Let's look at, let's try the 2008, I think. We'll do that one next. What is it? No, not 2008. Let's see, 2009. So look at the 2009 test. It was number 4, so it was also the first one in the non-calculator section that year. Yep, 2009, number 4. Alright, so I'm going to give you all about 15 minutes to try this one on your own. And we'll see how you do. And then we'll go over it.